Hello, and welcome to this talk on the communication complexity of collision. I'm Siddharth Jain, and this is joint work with Mika Yus. So, the main result of this work is a communication complexity lower bound for a natural two-party version of collision. So, let's revisit what the collision problem is. In the collision problem, we're given n numbers written in binary. And we're promised that this list is either one to one, which means that every number is unique, or it's 2 to 1, which means that every number occurs exactly twice in this list. This problem was initially defined because it was motivated by cryptanalysis, and it has been very well studied in literature. In the black box model or the query model, where when we ask for an index I, we're given the log n bits which denote the number in the ith index, we understand its complexity quite well. In particular, we know that its randomized query complexity is root n up to constants. And we know that in the quantum setting, we can get a polynomial speed up, and that's detected. So now if you want to study this problem in the communication setting, what are the natural ways to split the input between the two parties, Alice and Bob? Well, one natural idea is to just split the lists in two and give them to Alice and Bob. Unfortunately, this leads to a trivial communication problem, and I'll leave it as an exercise for you to figure out why. So what do we consider? We consider a problem that we call bipartite collision. In this problem, what we do is that we take the binary encoding of the numbers and split them between Alice and Bob. So we get two lists by splitting the inputs in two, and we give each list to Alice and Bob. And when I say split, I really just mean take a number with an even number of bits in its representation, and give the first half to Alice and the second half to Bob. And to reiterate, the question we ask is how much communication is needed between Alice and Bob to decide this bipartite collision problem? Our main theorem is that there is a polynomial lower bound on the randomized communication complexity of this bipartite collision problem, and this lower bound applies even to quantum communication. So let's now discuss a very popular method to prove communication lower bounds, which is called lifting. In lifting, given some f, function f, which you do know a query lower bound for, you wish to get a communication lower bound for it. And to do so, you compose it with some small gadget, G, to create a two-party problem. So formally, what I mean is the following. And the issue with this is that by design, you get a very artificial problem by this method. To see why, let's consider the case of XOR. When G is XOR, then Alice and Bob both receive n-bit strings, and the true string corresponding to the input list in this case is the bitwise XOR of these two strings, which seems like a very unnatural way to distribute the input between Alice and Bob. And a priori, it's not at all clear how you would relate it to the very natural problem of bipartite collision. So, nevertheless, let's see a very clever reduction for the case of XOR by IR20. So this is just the setup. We have two lists, A1 to AM and B1 to PM. And we want to find two indices, I and J, such that AI plus BI is equal to AJ plus BJ. And I'm here now just overloading the plus symbol to mean bitwise XOR. So the reduction works as follows. In the reduction, Alice and Bob both map their inputs, each element in the list, to an ordered list. And what I mean here by plus C in square brackets is that We just add every possible binary string lexicographically to the element in the list. So I add 0 to the n to a1, then I add 0 to the n minus 1, 1 to a1, and so on and so forth, right up till adding 1 to the n. And the solution in this instance for the bipartite collision problem is the following tuple listed below. This tuple gives us two equations, which imply that we have a solution in the original input. Moreover, notice an additional property of this reduction. Fixing Z0, Z1 is unique. And what this gives us is that it preserves the one-to-one versus two-to-one structure of the input. So this is quite encouraging. We have a reduction for the case of XOR. But there is a caveat that we don't know any lifting theorems for XOR, and in fact, we can't hope to have them because we know counterexamples. But the claim here is that we're not really using the full power of XOR here in our reduction. All we really need is some properties that we call regularity. So with that in mind, let's discuss regular gadgets. To preface, our main contribution is that if G is a constant size regular function, which we use as a gadget to compose with the collision problem, we can reduce to bipartite collision with some polynomial blow. So what are regular functions? A bipartite function is said to be regular if there is a group acting on its domain, such that if you consider any element and say that it's mapped to some bit b by the function, then the orbit of this element with respect to this group is exactly the pre-image of that b. And the second property that we need is that for any two elements of this pre-image, there is a unique group element taking the first to the second. So to concretize this, I claim that XOR is regular. And this is just because you can take the following two operations, identity and the NOT operation on both inputs at once. And this witnesses that this function is regular. So hopefully now it's becoming clear that we're really just using the regularity of XOR in the reduction in the previous slide. So with that, let's say we believe that, then it just remains to find a function for which we can live. And it's also regular. Well, turns out this is already known. In 2011, Shurstoff proved that the versatile function lives approx degree to approx rank. We're just noting that versatile is actually a regular function, and I'll prove it to you by picture. On the left here, we have the matrix corresponding to the versatile function, which takes as input two integers mod 4 and output 0 or 1. And on the right, I have the generators for the group acting on the preimage of 1, which witnesses that this versatile function is regular. And for completeness, let me tell you what these operations are that I've listed in black and orange on the right. So that's it for the reduction and the lower bound for bipartite collision. Note that we have a small polynomial lower bound, and it is an interesting problem to close the gap between the upper bound and the lower bound for this problem. But we also have an application of this result to prove complexity. This is just through known relations to the communication complexity of search problems. And our contribution is to show a lower bound for a bipartite analog of the pigeonhole principle, which is natural in the same way that bipartite collision was. And here what I mean by the search problem corresponding to the pigeonhole principle is that I give you a list which is guaranteed to have collisions, just find one. So how do we do this? We do this by a simple search to decision reduction, which just involves appending a one-to-one list to the input for collision. So let's see what happens when we do that. On the left here, I have the input to collision, which is one-to-one in blue, and the appended list below in orange. And on the right, I have the same construction except the input to collision is 2-to-1. Let's zoom in on these vertices. So what's happening here is that in the first case, we only have one kind of collision, which is between a blue edge and an orange edge. But in the second case, we have two kinds of collisions. We have collisions between a blue edge and an orange edge as before, but we also have a collision between two blue edges. So the crux is that if we use the structure of collision and to permute our input in such a way that the algorithm which solves the pigeonhole principle problem outputs a random collision, then we can detect these blue to blue collisions with decent probability, which helps us solve our decision problem. So that's it. That's all I had to say. Thanks for listening.